This is the second of two videos that walks through a proof by mutual induction of a property of rooted trees. In the previous video, we did everything up until the inductive step, and so in this video, we're going to pick up where we left off and finish the inductive step. Let's begin by looking at the inductive hypothesis. Now, as usual, we imagine that we're selecting some arbitrary value n, and if this were a weak induction, that would be it. We would assume that our claim holds for n, and we would have to show that given that assumption, it holds for n plus 1. Remember, however, this is a strong induction, so you get to assume a bit more than that. In fact, you get to assume that it holds not only for n, but for every value less than or equal to n, but greater than or equal to our first base case, which in this case is 0. Sometimes we write that all out as the sequence 0, 1, n, but in this case we're just using k to represent all those possible values. Just as in our previous inductive proofs, whenever the inductive hypothesis applies, it means that we can assume the claim that we're trying to prove is already true for those cases. What's different in this example is that we're doing a mutual induction, so instead of just one claim, we have two. Both S sub 1 and S sub 2 hold as long as the object we're talking about, either a rooted tree list or a rooted tree, has a derivation height of k, where k is some number in this range we've defined between 0 and n inclusive. Just so we don't forget what these statements S1 and S2 actually mean, it may be nice to keep a note handy. Remember that the statement about rooted tree lists says we're trying to prove the number of edges in the list is equal to the number of nodes minus the length of the list, and the statement about rooted trees is we're trying to prove the number of edges in a tree is equal to the number of nodes in the tree minus 1, and that second one is our actual theorem. Now, using our inductive hypothesis, we want to move on to establish the inductive step, and that means we want to show that S sub 1 and S sub 2 are both true at derivation height of n plus 1. We will start with S sub 2, and then after, we'll go back and prove S sub 1 also. Now, again, the expression S sub 2 of n plus 1 is really just a shorthand for the claim that if we have a rooted tree with derivation height of n plus 1, then the number of edges in that tree is equal to the number of nodes in that tree minus 1. So to demonstrate that that is true, we can start first by assuming that we do have such a tree. We have some tree T with derivation height n plus 1, where n is greater than or equal to 0. To understand what this gets us, we need to look back at the post system that we used to define rooted trees. One thing we know is that if t has a derivation height of n plus 1 with n greater than or equal to 0, then the derivation height of t certainly is not 0, so it was not formed by some axiom. What that means is that it was formed by either Rule 1 or Rule 2. Out of those two rules, however, only Rule 2 actually gives us a rooted tree. Rule 1 produces a list. So we know for sure that our tree t must have been produced by rule R2 and that it has a height of n plus 1. We also know that t can be written in the form node L, where L is the rooted tree list that we used in rule R2 to create t. Adding these facts to our proof, we say the derivation of t must end with rule R2, and also that it has the form node L, where L is some rooted tree list. It's useful to write t in terms of L because if you look back at the post system again, you can see we also know something about L. Namely, that if t has height n plus 1, L must have height n. This is because in rule R2, there's only one variable in the antecedent, so whatever rooted tree list we choose, it has to have a derivation height of 1 less than the tree we produce from it. That's good news, of course, because our inductive hypothesis will hold for a rooted tree list with a derivation height of n. And so combining all these facts together, we can now show that a rooted tree of height n plus 1 will have a number of edges equal to the number of nodes minus 1. The final piece of the argument goes like this. First, we know that the number of nodes in our rooted tree, which we're calling node L, is equal to 1 plus the number of nodes in the rooted tree list, L. Notice that on the left side of this equation, we're talking about the number of nodes in a rooted tree, and on the right side, we're talking about the number of nodes in the rooted tree list from which we created that rooted tree. There's no fancy logical inferences behind this equation. It just follows directly from the way we create rooted trees. Remember, what rule R2 says is that when we create a new rooted tree, we start with a list of rooted trees, which is what we're calling L. And to figure out the total number of nodes in this list, we just count up all of the nodes in each of the individual trees in the list and add them all together. And that's what number of nodes L means. When we create a new rooted tree from this list, what we do is we start with a new root and we connect it to all of the roots in the trees in the list. Every time we do that, clearly we are creating exactly one additional node. So the number of nodes in our new rooted tree will be 1 plus all the nodes that were in our original rooted tree list. And that is exactly what our equation says. This new tree is what we're calling node L. And the right side just writes the number of nodes in the tree, node L, in terms of the number of nodes in the rooted tree list from which it was produced. Hopefully the diagram makes clear why that is okay to do. So now that we have succeeded in expressing the number of nodes in our rooted tree in terms of the number of nodes in the rooted tree list that we're calling L, we can use our inductive hypothesis. Remember, L has a height of n, so the inductive hypothesis applies. What that means is we can assume that the number of nodes in our rooted tree list L is equal to the number of edges in that list plus the length of the list. Once we have that equation, all we're doing is just a simple substitution. To get to the next step, we have to look back at our definition and realize that the number of edges in the rooted tree list L plus the length of that list is equal to the number of edges in the rooted tree that we would form from that list using rule R2. To make sure that's clear, we'll go back to the example list L that we used before, and just as before we counted up the number of nodes in the whole list by counting up the number of nodes in each individual tree, we'll do the same thing here with edges. What we end up with is the sum of the number of edges in each individual tree, and that's what we're calling number of edges in the list L. The key insight here is that when we go to create our new tree from this list, node L, we have to create our new root and then connect it by an edge to the root of every tree that's in the list. This means we're going to have to add an edge for every item in the list, which means we're adding a total number of edges equal to the length of the list. So the number of edges in our tree, node L, is going to be the same as the number of edges in the original list plus the length of the list. So if that much is clear, hopefully it will also be clear that all we're doing here is substituting one expression for the number of edges in our tree for another expression of the number of edges in our tree. So if we've gotten this far, all that remains to be done is a little bit of arithmetic to rearrange the equation so it is in a form that matches the claim that we were trying to prove. And remember, node L is equivalent to the t that we started with, which has derivation height n plus 1. This means we've reached the claim we were trying to prove, and we've established the inductive step for S sub 2. So if you're following along with this closely, you might think, well, S sub 2 is actually our theorem from the beginning. So it sort of looks like we proved our theorem. Why do we need to do anything else? And the answer is we did prove S sub 2, but in order to do it, we relied on our statement S sub 1. So we also need to show that that statement is true. And that is the last thing we will do to complete the proof. The statement S sub 1 is a statement about rooted tree lists, and so we're trying to show that our claim is true for some rooted tree list where the derivation height is n plus 1. So just like last time, we'll start by assuming that we have some rooted tree list with a height of n plus 1. We'll call it L prime. And the fact that our n is greater than or equal to 0 tells us something important. It tells us that the derivation height of L prime is greater than or equal to 1. That means that it cannot have been produced by an axiom. And so if we look back at our post system for rooted trees, we can see that it could not have been formed by rule B. What this means is that it has to have been produced by R1 or R2, but if we look closely at R2, we'll see that only produces rooted trees and not rooted tree lists, so it cannot have been produced by R2, and this leaves just R1. That is the only rule that can produce a rooted tree list with height of 1 or greater. So therefore, we also know that our rooted tree list, L prime, was created using this cons operation on our two variables x and y. And so we can write L prime is equivalent to cons xy for some xy. To write this out, we can just say our derivation must end with rule R1, and therefore our L prime has this form cons TL, where T is a rooted tree and L is a rooted tree list. And I'm just using T and L here to indicate these are specific elements that we are plugging into our variables x and y to produce cons TL, which is our rooted tree list of height n+1 that we are calling L prime. Now that we've succeeded in rewriting our rooted tree list L prime in terms of the rooted tree T and the rooted tree list L, we can also say something about those two elements. In particular, at least one of them has a derivation height of n, and the other one has a derivation height of at most n. So just to illustrate how we know that, we can return to our rule R1, and you can see that if L prime has a height of n+1, and our elements T and L are in the antecedent of this rule, then at least one of them has to have a height of n. It's either T or L. And the other one has to have a height of at most n. It certainly cannot have a height of greater than n. And of course, its height will never be less than 0. So since we have set this proof up as a strong induction, that is enough to allow us to use our inductive hypothesis. And now we can pull these facts together to establish our claim. We start with the observation that the number of edges in the rooted tree list cons TL is equal to the number of edges in the rooted tree T plus the number of edges in the rooted tree list L. To convince yourself of this, I think you just have to remember what cons TL does. That we start with some list L, and then we add a tree to it to create a new list that is cons TL, or what we're calling our L primed. If you understand what's happening there, I think it's pretty straightforward to see that we get the number of edges in T by just counting up its edges, and we get the number of edges in L by counting the edges of all the trees that are in L, and then the number of edges in cons TL is just the sum of those two things. As we said, the derivation height of both T and L is greater than or equal to 0 and less than or equal to n, so our inductive hypothesis applies, and we can assume that the number of edges in T is equal to the number of nodes in T minus 1, and so we can substitute that in just using our statement S sub 2. Furthermore, we can also use our inductive hypothesis on L to conclude that the number of edges in L is equal to the number of nodes in L minus the length of L, and we can substitute that too. Here we're using our statement S sub 1. Now, in the next step, we can rewrite this expression as the number of nodes in cons TL minus 1 minus the length of L. There's nothing earth-shattering going on here, but we are doing a couple things at once, so I'll walk through the reasoning. First, we're just rearranging their -1 and our negative length of L so that they appear at the end of the line. Next, we're rewriting our remaining terms, the number of nodes in T plus the number of nodes in L, as the number of nodes in cons TL. And again, to see why this works, just look at the structure that we're talking about when we say cons TL. This is just a new list that we are forming from our tree T and a previously existing list L. You've seen a few variations of this by now, but hopefully it's clear that the number of nodes in this new list is going to be equal to the number of nodes in that tree T plus the number of nodes in all the trees in the original list L. The next step is easy. We just factor out a -1 from our last two terms to get -1 plus the length of L. Then we notice that that value is the same as the length of the list cons TL. And again, this is not deep, but it might take a little thinking through before it becomes clear. So once again, let's look at our list cons TL written so you can see the separate T and L that we formed it from. And hopefully you agree that if we add one tree to a list, we end up with a new list that is longer by 1. So its length is 1 plus the length of L. That's all we're saying here. But now that we have everything written out in terms of the number of nodes in const L minus the length of our rooted tree list const L, all we have to do is go back and remember that const L was the form of our rooted tree list L prime, which had the derivation height of n plus 1. If we substitute that in, we have proved our statement S sub 1. Now, to make it absolutely clear that we have done that, we'll just do a little bit of cleanup to put it in exactly the form that we originally stated it in. What we have shown through this chain of substitutions is that the number of edges in L prime is equal to the number of nodes in L prime minus the length of L prime. Now the right side of this equation is just a direct copy of the last line that we just derived. The left side, on the other hand, is a direct copy of the expression we began with, except we're replacing const L with L primed, which we know we're allowed to do. Finally, all we have to do is a little bit of arithmetic manipulation. We add the length of L prime to both sides, and we get exactly the statement S sub 1 that we're trying to prove. And so now that we've shown that both S sub 1 and S sub 2 are true, we have completed our proof by mutual induction of this theorem.